In the beginning, before the sun had kindled its furious light, before planets had gathered themselves into spherical certainty, there was only a vast, swirling cloud, a nebula, cold and dark, stretching across the silence of space. It hung suspended by the faint breath of cosmic dust, a delicate balance between gravity's pull and the restless dance of particles too small to be named. Here, in this cradle of shadow and possibility, the story of comets and meteors truly begins. Imagine for a moment the young solar system, some 4.6 billion years ago, before Earth had hardened its molten skin, before Mars had lost its rivers, before Jupiter had claimed its retinue of moons. The sun had only just ignited, a newborn star flaring into consciousness, its light sweeping away the last remnants of the nebular haze. In those early epochs, gravity became the silent sculptor, gathering motes of dust and ice, compelling them to coalesce, to clump into larger and larger bodies. Some fragments grew into planets, their orbits settling into the familiar clockwork we know today. But countless others, leftovers, wanderers, remnants too small or too distant to become worlds, remained as icy shards at the fringes of the newborn system. These ancient leftovers, untouched by time and unyielding to gravity's grand designs, became the comets, silent archivists of the primordial nebula. Their home is the distant Oort cloud, a vast spherical shell enveloping the solar system, stretching perhaps a light year from the sun, so far that the sun itself becomes but a distant ember. Here, trillions of icy bodies drift in the darkness, each no larger than a mountain, some scarcely larger than a city block. They are made of water ice, frozen gases, ammonia, methane, carbon dioxide, and dust, blackened by eons of cosmic radiation. In this deep freeze, time itself seems to pause, and the comets remain unchanged for billions of years. Yet sometimes, a passing star or the tidal pull of the Milky Way stirs the Oort cloud, dislodging a comet from its slumber. Gravity nudges it gently, then more insistently, until it begins the long fall inwards toward the sun, toward the realm of light and heat. As the comet journeys through the outer solar system, its icy heart remains intact, a compact nucleus, often just a few kilometers across, dark as coal and colder than the surface of Pluto. But as it nears the sun, the warmth begins its patient work. Gases trapped for billions of years begin to sublime, to transition directly from solid to gas, streaming outwards in a tenuous halo. The sun's radiation and wind catch these escaping vapors, sculpting them into a luminous, streaming tail that can stretch for millions of kilometers, always pointing away from the sun, as if the comet flees an unseen pursuer. The tail is an ephemeral thing, a glowing banner of dust and plasma. It is the comet's most theatrical moment, a moment that can stir awe and wonder in those who gaze up from distant worlds. Ancient peoples saw these apparitions as omens, harbingers of war or famine, symbols of celestial upheaval. Chinese astronomers recorded cometary visits as early as the 2nd millennium BCE, their observations inscribed in silk scrolls. The Greeks called them hairy stars, and the Romans feared them as portents of disaster. Yet in truth, these icy visitors are nothing but messages from the dawn of time. Their orbits and outbursts governed by the laws of physics as surely as the tides are pulled by the moon. One of the most famous comets in human history is Halley's Comet, a periodic visitor whose 76-year journey through the solar system has been chronicled for over 2 millennia. Its return in 1066 coincided with the Battle of Hastings, immortalized in the Bayeux Tapestry as a fiery omen streaking across the sky. Edmund Halley, the English astronomer, first recognized its periodicity in 1705, using Newton's new laws of motion and gravitation to predict its return. When the comet reappeared in 1758, Halley's reputation was secured, and the comet that bears his name became a symbol of humanity's growing mastery over the cosmos. But comets are not the only wanderers. There are the asteroids, rocky remnants left over from the planetary formation, most of them huddling in a broad belt between Mars and Jupiter. Some are large enough to be called minor planets. Others are mere boulders tumbling through the void. Occasionally, gravitational perturbations, perhaps a nudge from Jupiter or the collision of two bodies, will send an asteroid into an orbit that crosses Earth's path. Most of these are harmless, burning up as meteors in our atmosphere. A few, however, have left scars upon the Earth, reminders of the violence that still lurks in the heavens. And then, there are the meteor showers, celestial rainstorms that return with clockwork precision year after year, as the Earth plows through the debris left behind by comets. Each shower is named for the constellation from which its meteors seem to radiate. The Perseids in August, the Geminids in December, the Leonids in November. The Perseids, for instance, are the legacy of Comet Swift-Tuttle, which leaves a trail of dust and gravel as it loops around the Sun every 133 years. When Earth, racing along its orbit at nearly 30 kilometers per second, intersects this debris stream, the tiny fragments strike our atmosphere with tremendous speed, some 60 kilometers per second, igniting in brilliant flashes of light. These meteors are usually no larger than grains of sand, yet their speed transforms them into streaks of incandescence, momentary scars upon the night. The largest fragments can produce fireballs, bolides, that rival the brightness of Venus, sometimes ending in sonic booms or meteorites that reach the ground. The most famous recent example is the Chelyabinsk event of 2013, when a 20-meter asteroid exploded over Russia, releasing the energy of 500,000 tons of TNT and shattering windows across an entire city. Yet for all their violence, for all their drama, comets and meteors are also gentle teachers, offering us glimpses into the solar system's remote past. The European Space Agency's Rosetta mission, which rendezvoused with Comet 67P Churyumov-Gerasimenko in 2014, revealed a world of unexpected complexity, cliffs and pits, jets of gas spurting from fissures, organic molecules that hint at the chemistry of life. The Japanese Hayabusa missions, which returned samples from the asteroids Itokawa and Ryugu, have shown that these bodies are not solid rocks, but loose conglomerates, rubble piles, held together only by their own feeble gravity. Comets, in particular, may have played a crucial role in the origins of life on Earth. The Panspermia hypothesis suggests that comets, rich in water and organic compounds, may have delivered the building blocks of biology to the young Earth, seeding our planet with the raw materials for life. The impact that formed the Chicxulub crater 66 million years ago, ending the reign of the dinosaurs, was likely caused by an asteroid or a comet, its energy equivalent to billions of Hiroshima bombs. Thus, comets and meteors are both creators and destroyers, harbingers of life and agents of extinction, their dual nature woven into the fabric of our planet's history. But let us return to the beginning, to the far reaches of the solar system, to the Oort cloud and the Kuiper belt, the two great reservoirs of comets. The Oort cloud is a sphere, vast and diffuse, its inner edge perhaps 2,000 astronomical units from the Sun, its outer edge lost in the interstellar dark. The Kuiper belt, by contrast, is a flattened disk beyond Neptune, home to Pluto and Eris and countless smaller bodies, including the short-period comets whose orbits are measured in decades, not millennia. The dynamics of these regions are governed by a complex interplay of gravity, Jupiter's massive presence, the passing stars, the galactic tide, all conspiring to send comets inward or outward, to stir the cold embers of creation. Some comets, like Halley, become periodic visitors, their orbits reshaped by planetary encounters. Others are ejected entirely, cast into the interstellar void, lost forever to the darkness between stars. The mathematics of cometary orbits is a subtle science, requiring the tools of celestial mechanics developed by Newton, Laplace, and Gauss. The equations describe not only the paths of these bodies, but their changing speeds, their encounters with planets, the way their tails are sculpted by the solar wind and magnetic fields. Modern astronomers use massive surveys, such as the Pan-STARRS telescope in Hawaii and the Catalina Sky Survey in Arizona, to catalog new comets and asteroids, plotting their trajectories and assessing their potential threat to Earth. Yet, despite our growing knowledge, comets retain an aura of unpredictability. The Great Comet of 1843, for example, appeared suddenly, blazing so brightly that it could be seen in daylight. The comet Hale-Bopp, discovered independently by Alan Hale and Thomas Bopp in 1995, became visible to the naked eye for a record 18 months, its double tail fanning across the sky. There are comets with orbits so long, millions of years, that they may never return. And there are those like the sun grazers, that plunge perilously close to the sun, only to disintegrate in a final, incandescent gasp. Meteor showers, too, have their moments of drama. The Great Leonid Storm of 1833, for instance, when tens of thousands of meteors rained down per hour, convincing some that the world was ending. The science of meteor showers is a study in patience and precision, requiring astronomers to map the debris trails of comets, to calculate their intersection points with Earth's orbit, to predict the timing and intensity of each year's display. The shower's radiant, the point in the sky from which the meteors appear to emanate, is a function of perspective, a cosmic illusion created by the geometry of intersecting orbits. For those who watch from Earth, lying beneath a dark sky far from city lights, a meteor shower can feel like a private communion with the universe. Each streak of light is the last, incandescent breath of a fragment older than the pyramids, older than the continents themselves. The Perseids have been observed for over 2,000 years, their first recorded appearance in Chinese chronicles dating to 36 CE. The Geminids, a more recent arrival, originate not from a comet but from an asteroid, 3200 Phaethon, blurring the boundaries between categories, challenging the neat divisions of science. The boundary between comet and asteroid is, in fact, increasingly porous. Some bodies, like 133P Elst Pizarro, display both the rocky composition of asteroids and the outgassing behavior of comets, earning them the label main belt comets. Others, like Phaethon, may be extinct comets, their volatile ices long since boiled away, leaving only a rocky husk. The distinction between a meteor, a meteoroid, and a meteorite is one of context. A meteoroid is a small body in space. A meteor is the streak of light as it burns in the atmosphere, and a meteorite is what remains if it reaches the ground. The study of meteorites has become a science unto itself, revealing the composition and history of the solar system in microcosm. Some, like the Allende meteorite that fell in Mexico in 1969, contain calcium-aluminum-rich inclusions, tiny grains that are the oldest known solids in the solar system, dating back to its very birth. Others, like the Murchison meteorite, are rich in amino acids and organic molecules, fueling the debate over the cosmic origins of life. There are iron meteorites, remnants of shattered planetary cores, and stony chondrites, full of chondrules and pre-solar grains. The impact history of Earth is written in craters and extinction events, in the fossil record, and the layers of iridium scattered across ancient rocks. The Tunguska event of 1908, when a small asteroid or comet exploded over the Siberian forest, flattened 2,000 square kilometers of trees, yet left no impact crater, a reminder of the power that even small bodies can unleash. The Barringer crater in Arizona, Uwalin 200 meters across, was formed 50,000 years ago by a nickel-iron meteorite weighing 60,000 tons. Such impacts are rare on human timescales but common on geological ones, shaping the history of life and land. In recent years, the threat of cosmic impacts has become a focus for planetary defense. The Near-Earth Object Observations Program, operated by NASA and international partners, seeks to identify and track asteroids and comets that could pose a risk to our planet. Missions like DART, the Double Asteroid Redirection Test, have demonstrated the possibility of altering an asteroid's trajectory, nudging it gently away from a collision course. The data gathered by these missions is a testament to the ingenuity and vigilance of a species determined to survive in a dangerous cosmos. But for all the danger, for all the uncertainty, there is also beauty and wonder, a sense of connection to the cosmic past. The Rosetta mission's images of Comet 67P, its strange, twin-lobed shape, its jets and cliffs and shadowed valleys, evoke a landscape as alien as any in the solar system. The Stardust mission, which collected particles from Comet Wild 2 and returned them to Earth, revealed a mix of high-temperature minerals and organic compounds, evidence of the complex chemical processes that unfolded in the early nebula. The poetic resonance of comets and meteors has inspired artists and writers for millennia. In Shakespeare's Julius Caesar, comets are the heavens themselves blazing forth the death of princes. In the paintings of Giotto, the Star of Bethlehem is rendered as a comet, its tail a symbol of divine inspiration. The philosopher Immanuel Kant speculated that comets might carry the seeds of life between worlds, an idea echoed in the modern theory of panspermia. In the 19th century, the American poet Walt Whitman wrote of the comet that came unannounced out of the north, blazing through the midnight sky. Today we know so much more, yet the sense of mystery endures. The chemistry of comets is a field of active research, with missions planned to return samples from the nucleus itself. The study of meteorites continues to yield surprises: a new mineral, a strange isotope, a clue to the processes that shape the planets. The search for near-Earth objects is a race against time and probability, an effort to forestall disaster and understand our place in the cosmic dance. The story of comets and meteors is, in the end, a story of origins, a story that links the distant Oort cloud to the blue-green world we call home. It is a story written in ice and stone, in fire and shadow, in the fleeting brilliance of meteors and the slow, majestic arc of comets across the sky. It is a story of violence and creation, of destruction and renewal, of the infinite patience of the cosmos, and the restless curiosity of those who look up in wonder. The next time you see a meteor streak across the night, or glimpse the ghostly tail of a comet, remember that you are witnessing a fragment of the solar system's memory, a message from the time before planets, before life, before even the sun itself had found its voice. These wanderers, these messengers, remind us that we are part of a story that began in darkness and silence, and that continues, unbroken, in the light of every new dawn. In the deep cold reaches beyond Neptune, where sunlight is but a rumor and the stars shine with an ancient, indifferent light, the Kuiper belt lies in quiet anticipation. This region, discovered only in the late 20th century, is a flattened ring of icy debris, stretching from 30 to 50 astronomical units from the sun. It is here that short-period comets are born, comets whose orbits carry them around the sun in less than 200 years. Unlike the long-period comets of the distant Oort cloud, the Kuiper belt is home to Pluto, once considered the 9th planet, now reclassified as a dwarf planet, alongside Eris, Haumea, and Makemake. Yet, these names belie the diversity and complexity of the region. The New Horizons mission, which flew past Pluto in 2015, revealed a world of frozen plains, towering ice mountains, and a thin blue haze of atmosphere, features as unexpected as they are beautiful. Beyond Pluto, New Horizons encountered Arakoth, a contact binary composed of two lobes gently joined during the solar system's infancy. Its smooth, undisturbed surface suggests it has remained largely unchanged for over 4 billion years, a time capsule from the era when planets were still assembling from dust and ice. Comets from the Kuiper belt are jostled from their orbits by the gravitational influence of Neptune and the other giant planets. Once ejected, they become Centaurs, icy bodies that cross the orbits of the outer planets, their destinies uncertain. Some are captured by Jupiter, their paths bent into short-period orbits. Others are flung outward, lost to the darkness. The study of Centaurs, such as Chiron and Chariklo, has revealed the presence of rings, delicate structures once thought unique to the giant planets, hinting at a complexity of processes yet to be fully understood. As comets approach the inner solar system, their transformation is both chemical and physical. The heat of the sun penetrates the surface, causing volatile ices to vaporize and escape. The escaping gas drags dust particles with it, forming the coma and the characteristic tails. The gas tail, composed of ionized molecules, glows blue under the influence of ultraviolet light, while the dust tail reflects sunlight, appearing white or yellow. The interaction of the solar wind with the comet's ion tail creates a shock wave, a bow shock, similar to the wake of a ship moving through water. The tails of comets are not merely beautiful, they are laboratories for the study of physics and chemistry under extreme conditions. The spectra of cometary comas reveal the presence of water, carbon monoxide, cyanogen, and a host of organic molecules. The detection of glycine, an amino acid, in the coma of Comet 67P by the Rosetta spacecraft, has profound implications for the possibility of life elsewhere. The isotopic ratios of hydrogen and oxygen in cometary water provide clues to the sources of Earth's oceans, fueling debates that continue in scientific journals and conferences. Meteor showers, too, are more than spectacles. They are opportunities to study the composition of cometary debris and the dynamics of Earth's atmosphere. Radar observations track the influx of meteoroids, measuring their velocity and ablation, the process by which they burn up. High-speed cameras capture the fleeting trails, allowing scientists to reconstruct their trajectories and determine their parent bodies. The study of meteorites that survive the journey to Earth's surface, collected from the deserts of Antarctica and the sands of the Sahara, has revealed pre-solar grains, tiny particles that predate the solar system itself, formed in the outflows of dying stars and supernovae. The science of comets and meteors is a window into processes that shape not only our solar system, but planetary systems across the galaxy. Observations of other stars have revealed disks of dust and debris, protoplanetary disks, where comets and asteroids are still forming. The discovery of exocomets orbiting distant stars, detected by the dips in starlight as they transit their host, suggests that the phenomena we observe here are universal, a consequence of star and planet formation everywhere. Yet, for all the advances in observation and theory, some mysteries persist. The great debate over the origin of the Oort cloud continues. Was it formed in situ, or were its comets scattered outward by the migration of the giant planets? The question of whether comets delivered the water of Earth's oceans remains unresolved, with isotopic measurements offering conflicting answers. The frequency and severity of cosmic impacts, and their role in shaping the evolution of life, are subjects of ongoing research, their answers hidden in the rocks and ice of distant worlds. The emotional resonance of comets and meteors is perhaps best understood as a reflection of our own impermanence. The fleeting passage of a meteor across the sky, the slow return of a comet after centuries of absence. They remind us that we are part of a universe in motion, a universe where change is the only constant, where creation and destruction are two sides of the same cosmic coin. In the ancient city of Babylon, priests watched for comets and meteors, recording their appearances as omens and portents. In the courts of imperial China, astronomers kept meticulous records, their observations preserved for millennia. The philosopher Aristotle sought to classify comets as atmospheric phenomena, a view that persisted until the work of Tycho Brahe and Johannes Kepler in the 16th and 17th centuries. Newton's Principia, published in 1687, provided the mathematical framework to understand their orbits, transforming superstition into science. The 20th and 21st centuries have seen a renaissance in the study of small bodies. The Giotto spacecraft, launched by the European Space Agency in 1985, became the first probe to fly past the nucleus of a comet, Halley's Comet, in 1986. It returned images of a dark, peanut-shaped body, its surface scarred by jets and pits. NASA's Deep Impact mission in 2005 launched a projectile into the nucleus of Comet Tempel 1, studying the composition of the ejected material. The Epoxy mission, which revisited Tempel 1 in 2011, observed changes to the surface caused by outgassing and solar heating. The Japanese Hayabusa and Hayabusa 2 missions have returned samples from asteroids Itokawa and Ryugu, revealing a surprising variety of compositions and structures. OSIRIS-REx, a NASA mission, has sampled the surface of asteroid Bennu, a rubble pile whose loose structure is held together by weak gravity. These missions are not only feats of engineering, but windows into the earliest history of the solar system, each sample a chapter in the story of creation. The future of cometary and meteoritic research is bright. Missions are planned to return samples from the surface of a comet to study the chemistry of their ices and the structure of their nuclei. The Vera C. Rubin Observatory, currently under construction in Chile, will survey the sky with unprecedented sensitivity, discovering new comets and asteroids, tracking their paths, and perhaps detecting the first interstellar visitors to our solar system. The detection of Oumuamua in 2017, a cigar-shaped object passing through the solar system on a hyperbolic trajectory, reminded us that the cosmos is full of surprises. Its rapid rotation and unusual shape, its lack of a visible coma, sparked debates over its origin and nature. Was it a fragment of a shattered planetesimal, or an object ejected from another star system? The discovery of Borisov, the first confirmed interstellar comet in 2019, confirmed that such wanderers are not unique. These interstellar visitors carry with them the chemical signatures of distant suns, linking our solar system to the wider galaxy. In the poetry of science, Comets and meteors are the punctuation marks, the exclamation points and ellipses, reminding us that the story is never finished, that new chapters are always being written. They are the messengers of the cosmos, bearing witness to the processes that shaped our world and the worlds beyond. In contemplating their origins, we are drawn to reflect on our own. The atoms in our bodies were forged in the hearts of stars, scattered across space by supernovae, gathered into the dust and ice that became the planets, the comets, the meteors. We are, in a very real sense, the children of cosmic wanderers, our history written in the language of chemistry and physics, our future bound to the rhythms of the heavens. The night sky, with its constellations and shifting lights, is a reminder of the vastness of time and space, and of the continuity that links past, present, and future. The next time you see a meteor flash across the darkness, or glimpse the ethereal tail of a comet, remember that you are witnessing a fragment of cosmic history, a message from the edge of creation, a story billions of years in the making. The study of comets and meteors is not only a scientific endeavor, but a journey of wonder and discovery. It is a testament to the curiosity and ingenuity of a species that dares to ask questions, to seek answers, to explore the unknown. It is a story that belongs to all of us, a story that continues with every new discovery, every new observation, every new moment of awe beneath the stars. In the end, the comets and meteors are not merely visitors to our skies. They are reminders of our place in the universe, of the fragile beauty of our world, of the endless possibilities that lie beyond. They invite us to look up, to dream, to remember that we are part of something vast and ancient, something that began long before us and will continue long after we are gone. Let the story of comets and meteors be a reminder that the universe is not a finished thing, but a work in progress, a canvas on which new wonders are painted with every passing night. Let it inspire us to keep searching, to keep questioning, to keep reaching for the stars. For in the end, it is not the answers that matter most, but the questions, the endless, unanswerable questions that draw us ever onward, into the darkness, into the light, into the story of the cosmos itself.